Welcome to my talk on explaining success in sports competitions, paired comparison methods with explanatory variables. I'm filling in today for Gerhard Tutz, who actually was supposed to give this talk today. He can unfortunately not be here, so I'm filling in, which has mainly two consequences. The first consequence is you're missing out on an impressive mustache that Gerhard has, and I obviously don't. And the second consequence is all the errors you might see in the slides are his and not mine. Okay, and so the work I'm showing you is joint work of Gerhard and me, and also in parts in collaboration with Andreas Groll. Okay, so let me tell you what I want to tell you today. I want to, convince you that paired comparisons are a sensible way to analyze sports data, because almost every sports competition can be seen as a paired comparison. I want to show you the basic models. I want to show you which types of covariates there might be and how you can include those covariates, and how we propose to estimate those models by using penalized regression methods. Okay, so first of all, what are paired comparison data? Well, paired comparison data always appear if you have a large set of objects, and then you take two of those objects and you compare them with respect to some latent trait that you cannot observe directly, okay? So that is traditionally from like psychometrics or sociology. So you do an experiment. So maybe you have like 10 wines and you want to know what is the best of those wines. Then you can do an experiment where you give each participant 2 wines, and he only has to decide which one is better, okay? He only has to compare 2 of those objects, and then he does that with another pair and with another pair, and you have many participants, and finally, with those informations, you can get a ranking of your wines, okay? And we think that sports competitions can also be seen as paired comparisons, because the unobservable latent trait that you have in that case is just the playing ability, okay? You compare the playing abilities of 2 tennis players to football teams, and you cannot observe that playing ability directly, but you can observe, well, if the first team wins or the second team wins, okay? So you have 2 cases. You could have a binary response or an ordinal response, which means, well, in tennis, you only have a binary response because either the first wins or the second one wins, okay? We have no draws. In football, obviously, we at least have 3 categories, because we have the win of the first team, a draw, the win of the second team. In our applications, we always use 5 categories, so a clear win for the first team, a win with 1 goal margin, a draw, and so on. Okay? So that is what you observe. What is the simplest model to estimate or to work with that kind of data? It's called the Braided model. So let's for now assume we have this binary response. Then the probability that the first team wins is simply modeled by a logistic regression model, okay? That's an easy model. You have all seen that. It's a logistic regression model. The interesting thing is then the linear predictor in this logistic regression model, which is simply the difference of the 2 abilities or strength or adjunctivities, whatever you call it, of the 2 objects that compete, okay? In sports, that means that's the ability of the first team, that's the ability of the second team, okay? And what we estimate are exactly those parameters gamma, okay? You estimate 1 parameter per team or per player. Then I think it's clear. if gamma R is equal to gamma S, if the two competitors are equal, then this difference is 0, the probability is 1/2, okay? If both teams are equal, probability that the first team wins should be 1/2. If gamma R is greater than gamma S, then there's a positive value in this linear predictor, and the first team has a higher probability to win than the second team, okay? That's very easy. It's getting a bit more complicated if we have ordinal responses. So that's the example I told you before. We use, for football data, always 5 categories. Then you model the probability, a cumulative probability that it's lower or equal to some value k, okay, which could be 1, 2, 3, 4. And then again, the linear predictor is basically the difference of the two abilities, and additionally a threshold parameter that separates the single response categories. Okay, maybe that's a bit fast how to justify that model, so I want to say a few things about the assumptions that are behind this model. The main assumption is that each object, in our case each team, has this unobservable random utility. And that is composed of an ability parameter that is fixed and some noise, epsilon. So we assume some distribution function for this noise, and the assumption now is that, well, we obviously cannot observe that because it's unobservable, but what we can observe is that this paired comparison between R and S ends with a K, okay? And then we assume that this means that the difference of the two utilities is between two threshold parameters, okay? So we assume that we observe a coarser version of what is actually behind it. So if that is the case, if we always observe only if the true difference is between two threshold parameters, that means that y is lower or equal to k if the difference is lower than this upper bound. If we plug in the definition of US and play with the equation, that means that we observe lower or equal to k if the difference of the noise is lower or equal to that expression, which is, again, exactly the linear predictor that we've seen before, okay? And now we take the probabilities of both sides, which simply means it's, well, yeah, a cumulative distribution function. So we take, for this value, the cumulative distribution function of the difference of the two noises, and that is then equal to this cumulative probability. And this can be basically any mostly symmetric distribution function, or a distribution function from a density with a symmetric density. And if we use the logistic distribution function, then we end up with the model that I've shown you before. Okay. What does that mean? Well, graphically speaking, you can imagine the model like that. You have a distribution of the difference of the two utilities. You estimate the 4 threshold parameters, because now we're talking about 5 categories, okay? You need 4 thresholds. And then simply the probability that your response is 2 is the area between those 2 threshold parameters under the density, okay? In that case, we have a case where gamma S is obviously smaller than gamma R, okay? The difference is negative, which means the first team is better than the second team. And that is intuitive because now you can see the two results that are preferable for the first team, which is 1 and 2, okay? Because in those two cases, the first team wins, have pretty high probabilities compared to the corresponding results on the other side, okay? And if we have that the other way around, now the second team is better, now we have a pretty low probability that the first team has a high win and also a low probability that it has a win with 1 goal margin. Okay? So, one more thing about this model. We always use restrictions for the threshold parameters. The restriction can be written down like that, but I think it's easier to just imagine what that means for like 5 categories, okay? It simply means that the lowest threshold and the highest threshold are symmetrical around 0. And the second highest are also symmetric around 0. That means if we switch the order of the teams, okay, if we go from RS to S place R, the probabilities are symmetric, okay? R plays S, and we have a probability of 1. That's equal to S plays R, and we have a probability of 5. And the same for 2 and 4. So probabilities are symmetric. So we can switch the objects, which is important for many other applications in paired comparisons, because you don't want to have an effect of which is first or which is second. In sports, actually, you might have guessed that is actually not true, because we do have an order effect, okay? Because the team that is named first is usually the team that plays at home, okay? And it makes a difference if we have Bayern against Dortmund or Dortmund against Bayern, okay? It should make a difference. And therefore, we include a further parameter, which we call delta. It's just a constant that we estimate. And basically, you can say that this delta increases the ability of the first named team. And if it increases the ability of the first named team, that's just the value that, well, is given to any home team for free, basically. Okay, so what we end up now is this model, or a model with this linear predictor. We have a home parameter, the threshold parameters, and all the ability parameters. So obviously, if that is equal to 0, there's no home effect. If this is positive, what we expect it to be, then you can just say that delta can be added to gamma R for that particular paired comparison, and increases the probability for good results for the first team. Okay, so that is now a first model that is a sensible model that we can directly apply to sports data. In our case, the application is always to data from the German Bundesliga. So we estimated that model for the season 15-16. We estimated the threshold parameters. It's not too important how they look. Well, we estimated the home advantage. As you can see, it's a positive value. So we have a home advantage actually in the Bundesliga. And most important, we estimated all the ability parameters, so 1 ability per team. So what you could do now, for example, is compare the ranks of our estimated abilities to the true final ranks from the table. And you can see it's very, very similar. We have some switches of single teams, for example here, Leverkusen and Gladbach, or I don't know, Darmstadt and Hoffenheim. But, well, mostly the ranking according to the estimated abilities and the true ranking coincides. Okay, but I mean, true is also relative because you could use 3 points for a win or 5 points for a win. So that is not, well, the last answer maybe to ranking football teams. Okay. So that was basically the introduction, how to get to a simple model that, well, takes care of all the most important issues in paired comparisons. But now we have the goal to include further explanatory covariates that might help us to explain why this team has a good ability and why another has a bad ability, okay? So the first very simple ad hoc approach was to use those estimated abilities I've shown you before and, for example, plot them against another variable of the teams, which is in that case the budget. So we have Bayern Munich here, who have the highest ability and the highest budget. And now you can, for example, fit a linear regression model or an additive regression model. And you would certainly see that the higher the budget, the higher the ability. But that is not actually what we really want to have. We find that a bit, well, it's not too elegant to have a two-step approach, to have one model to estimate the abilities and then to go to a second model to include your covariates. So we want to do that in one single model. And we've seen that there might be a whole lot of different variables, also variables that characterize the teams and the matches, or only the teams or only the matches. So we want to find a new way to incorporate all that into one model. So one little example of covariates that we want to use are what we call on-field covariates. That is an application I'm going to show you later in more detail. What we have are those variables like shots on goal, the number of shots on goal, the distance that each team runs, the percentage of ball possession, and so on, for each match in the whole Bundesliga season. And the goal is to link those those covariates to the abilities of the teams, which means, well, for example, if the distance that the team runs is higher, then the ability of the team is higher, okay? So we want to make use of different kinds of covariates. We want to link them to the explanatory variable, which is the match outcome, all in one paired comparison model. But a very important point is also to keep the model still sparse and interpretable, because you might see then a whole lot of new coefficients that are, well, basically way too many coefficients to interpret. And the way to go to that model is first to go from this model, the very simple model that I've shown you before, to a second model that is different from the first model, basically by the introduction of a new index I. So I've told you before that we always are talking about objects and paired comparisons that are compared to each other. But in each paired comparison, you can also find a subject. I've told you the example of the wines, okay? People taste wines and they find the first one better or the second one better. Then the person that tastes the wine is the subject of that comparison, okay? It's always the unity that does the comparison between the two objects. Okay, and this unity might have covariates, okay? The person may be male or female, it may be old or young, okay? And those characteristics of the subject of the person may have an effect on which wine it likes or does not like, okay? So the main message is that those ability parameters might depend on the subject that does the comparison. In sports, the subject is, well, the match or the match day, okay? So the abilities might be different from one match day to the other match day. Okay, that's just the main change that we start with now. And now we have different possibilities how to actually model this ability of team R on match day I. Okay. Well, I've told you about the subjects. If we are back in the wine example, then this variable, this vector x would collect all the variables that we know about the persons, okay? There would be age or gender and whatever we know about them, okay? And then age, for example, might have a different effect for the first one than for the second one, okay? We estimate parameters beta r that are different across the wines. And in sports, well, it's pretty similar. We might have circumstances xi, like the temperature, or if it's raining or not, or simply the time of the year, that are equal for both of the teams, okay? Because they are characteristics of the match. And then you can include that via this formula, okay? You have a basic ability beta r null, a team-specific intercept, and some team-specific effects if, for example, the team is better when it's raining or not. Okay? So we have circumstances that are equal for both teams, and we have team-specific effects in that case. Second, we might have covariates that not only vary over the matches, but both over the matches and the teams. Okay, I've shown you before the examples of those on-field covariates. The distance that a team runs is different for all the teams, but it's also different on each match day, okay? Therefore, we collect that in a vector set IR, okay? It's different for matches and teams. The model or the term that represents the ability is pretty similar. We have, again, a team-specific intercept, and we include those match team-specific variables with that term or with that term. The difference is, well, if set is the distance that a team runs, that might have an equal effect in the whole Bundesliga, okay? The distance has an equal effect for Dortmund and Bayern and Freiburg, or it might even be different across the teams. Freiburg might have another distance effect than Munich, okay? So that is the second possibility. The third possibility is that the explanatory variable is only variant across the teams, okay? I've shown you before the example of the budget. Well, the team has one budget across one season. It does not change across the matches. And I might be interested in how does the budget affect the ability of a team. So it looks like that. We have parameter tau, we call in that case, which is not team-specific, obviously, because, well, if all the budgets are different, then you need to have an equal effect for all the teams that, well, tells you the effect of the budget. Unfortunately, we can, at least with maximum likelihood methods, not estimate that model because those two effects are not identifiable, okay? You can't identify the intercept away from those only team-specific variables. You have infinitely many solutions, but later when I tell you about the penalty terms that we use, you will see that there are actually possibilities to separate those two effects. Okay. So those are the three possibilities of covariates that might be within a paired comparison. And it's not that you only use in one model only team-specific variables, and in the other model, only the match-specific variables. You can also combine that to a joint model. And the way we want to estimate that is via penalized likelihood estimation. Okay, I've told you before, well, one problem is certainly the huge number of parameters in the one application of the on-field covariates. We have 8 of those covariates. We would estimate 1 parameter per team, which are 18 teams. Well, there's a restriction of -1, but still we would end up with 136 free additional parameters in that model. And that's too much to interpret, but also probably a total overfit of the model, okay? We are almost in fitting each match specifically, so we are not actually explaining relations, but we are explaining the data, well, exactly. And that's really not what you want to do in statistics. So what we do is we replace the normal likelihood that we would have optimized in maximum likelihood estimation by a penalized version, where you have a penalty term J that, well, let's for now say penalizes some of your parameters in your model, and this is tuned by a tuning parameter lambda, okay? You probably have seen something like a rich type penalty or a Lassoo type penalty. That is pretty much the same. It's just that those penalty terms look a bit different than in simple rich or Lassoo penalization. Okay, how could this penalty look like? Well, let's go back to the first model that I've shown you, the very simple model without covariates. In that case, we did an application where we used this fusion penalty. And a fusion penalty is a penalty where you penalize absolute differences. If you penalize absolute values, that means if the penalty is very high, then those absolute values can be exactly 0, which means the difference is exactly 0, which means the two abilities of the teams would be equal, okay? And that allows us to get clusters of teams that don't actually need separate ability parameters because they are so similar, but they can share the same ability parameter, okay? We get clusters of teams with equal strength. So, how does that work? Here is a graphical representation of all the strength parameters that we estimate, depending on how much penalization we use, okay? Here is the penalty term. On the right-hand side, we have an unpenalized solution. That's just the solution that I've shown you in one of the first slides, well, except that it's another season, but it's the corresponding solution, so each team has its own ability parameter, okay? And then from the right-hand side to the left-hand side, we increase the penalty, we force the ability parameters towards each other, and we see, for example, here also already with the very low penalty on the parameters, the model tells us basically that Red Bull, Hoffenheim, and Dortmund don't need separate ability parameters. They are so similar in their ability that we can go further with one joint ability for them, okay? Then there's this huge cluster of teams. They all are forced to a joint ability and so on. And if we go on with that, well, we end up with a league where all the teams have the same ability, okay? And now the task is, you can see that as many different models that you can choose from. Which of those models has the best predictive power? We did that by cross-validation, and so this dashed red line just tells you, well, this is the model that we chose at the end because it has, in cross-validation, the best predictive power, okay? And so we end up with a model with 4 clusters of teams. Bayern and Darmstadt are clusters of their own. We have this Red Bull, Hoffenheim, Dortmund cluster and a huge cluster of teams in the middle of the league. Okay, that is one possibility. How would we, or could we, there are many possibilities, but what would our preferred way be to estimate the model that I've shown you before with the on-field covariates? Again, this is the model that I'm talking about. We have team-specific intercepts, and we have those set vectors that collect the distance, the ball possession, and so on for both of the competing teams. And for now, we allow for team-specific effects, okay? So it's alpha R and not alpha, so that Bayern might have a different effect than Borussia Dortmund, okay? So that's the model I'm talking about. And what we would suggest here is to use 2 penalty terms, a fusion penalty for the home effects and a fusion and selection penalty for the covariate effects. Well, the fusion of the home effects works basically the same as you've seen before with the ability parameters, with the intercepts. You penalize the absolute differences of all home effects of all teams. So with no penalization, each team has its own home effect, and then you get clusters of teams with equal home effects, and in the most extreme case, all the home effects are equal, so we have a global home effect again, okay? And the fusion and selection for covariate effects is also very similar. We again have differences. So we take, for example, all the distance effects, and we shrink all the distance effects for Bayern and for Dortmund and for Freiburg together. There might be clusters of distance effects across different teams. But we also include a simple Lassoo penalty on all those parameters, though the parameters, not only the differences can be set to 0, but also the parameters themselves, okay? So if distance doesn't even play a role, then all the parameters according to distance can also be set to 0 exactly, okay? And that basically is a data-driven way, at least if you use cross-validation, to find out how complicated does the model have to be, and what is a model that is too complicated and it's overfitting, okay? So that's basically what I told you. If we would have a very, very large tuning parameter, which means a large penalization of those 2 penalty terms, well, all the home effects across the edging teams are equal. All the covariate effects are simply 0. And so that term simply is eliminated, and delta R is going back to just being delta. And then we end up with the model, the first model that I've already shown you, okay? So that's the least complicated it can get. We will always have at least this model, but we might have covariate effects that increase our predictive probability in that case, okay? Yeah, and that is basically finally the way how to choose the tuning parameter that I'm always talking about. I'm not going too much into detail. Well, we cross-validated, which means we have very many different models. Because we have a grid of tuning parameters, we estimate the model for each of those tuning parameters. And then we cross-validate, which means we partition the data set into, well, for example, 10 parts. We use 9 parts for training. We use the last part for testing. And we do that in a circular way. in that case, with this, well, prediction measurement, it's not too important what you use there. It's nice because it uses the ordinal structure. In our case, you could also use the likelihood, for example. Okay, so what are the results if we want to estimate the model that I've shown you before and we apply those penalty terms that I've shown you, okay? It's an application to those data from 2015-16, and again, those are the 8 covariates that we are interested in. So we know the total amount of kilometers run by each team in each match, the percentage of ball possession, the rate of won tacklings, the total number of shots on goal, the percentage of passes that reach your own teammates, the number of fouls, and the number of offsides. That is just a short picture for how the cross-validation looks like. This is the least complicated model. This is the most complicated model. And this is the prediction error, okay? We choose the model with the lowest prediction error. And you can clearly see it's really not a good idea to do maximum likelihood estimation here, okay? Because we have a huge prediction error because it's a totally overfitted model, okay? We really need to structure our linear predictor in that case, okay? And what you end up with are those pretty coefficient paths for all the effects that we have in our model, okay? We always have a low penalization on the left-hand side and a very, let me start again. We have a very high penalization on the left-hand side and a no penalization on the right-hand side. So let's look at some of those pictures in more detail. Home effect, as I said before, we fuse all the home effects. So we start here with team-specific home effects. Then we get clusters of home effects. Okay, if we would stop here, we would have 2 clusters in the Bundesliga with a little bit higher home effect and a lower home effect. But the best model is this one, which simply tells us that all the teams share the same home effect in that model. Then let's look at distance in more detail. Distance is actually the one of the 8 covariates that has really the highest of all the effects. So it's positive for all the teams, which means, well, a better running performance is strongly associated to a better result or a better ability of the team. And again, well, all the teams share the same effect of distance in that case. An interesting case, in my opinion, is ball possession, which has a negative effect. So the higher your ball possession, the lower your ability in that particular match, okay? So we had discussions on how to exactly interpret that. We basically finally came up with the explanation that maybe football really changed in the last like 5 years or something, that you have, well, you're focusing on fast counterattacks. It's not really that helpful to have the ball for a long time, but to get the ball in a good position and then have a fast counterattack, which maybe does not then lead to high values of ball possession. But, well, maybe one should not overinterpret that. Yeah, those are just 2 examples I wanted to show you out of those covariate effects. You can see all the other effects here. I'm not going into too much detail here. Yeah, I'm not going to talk about that. Just a short picture also about the intercepts. So this is basically the abilities that we start with a very high penalty. and then as the covariates get into the model, also the abilities spread out, okay? The scale of the abilities then increases because, well, in total there's more explanatory power in your model now. Okay. So much on those on-field covariates. The last thing, the last penalization technique I want to show you is on how to include pure team-specific explanatory variables, okay? I've told you before that if we have something like budget, which does not vary over the matches, but only over the teams, we cannot actually identify those two effects, but we can actually then estimate it if we impose further restrictions, okay? And a penalty term is nothing else than a restriction, okay? We restrict those differences. That is enough restriction for the model to be identified or for the model to be estimable again, at least, okay? So what you could do is simply apply the same penalty term as the penalty term that I've shown you first, okay, by clustering all the abilities. So you cluster the abilities, you just force them to be more similar than they would have been in maximum likelihood. And then you can easily include something like budget or market value, and you can estimate that. Additionally, you could also penalize the covariate effects themselves there, but, well, it's only sensible if you have really many of those team-specific explanatory variables. There's one example I want to show you again from the Bundesliga. What we did is we collected the market values of the teams, in that case not of the starting 11 per match, but simply the market value of the team across the whole season or at the start of the season, basically, okay? So we want to know how does the market value affect the ability of the teams. And we do not penalize the market values itself, but we only penalize the differences of those ability parameters. So we would start with a high penalty here where all the teams have the same ability, and we have a very high impact of the market value because the market value is the only thing that can explain anything in this model now. And then we might have different clusters of teams. Okay, this is now not cross-validated, so I can't actually tell you which one is the best in predictive performance, but maybe it could be this one. Okay, we would have, again, 4 clusters of teams with different abilities, and then we would have, like, that market value effect, okay? So by this penalization term, it's also possible to make such a model identifiable. Okay. Only a few words at the end of my talk about the whole framework and the package that contains this framework. So we wrote an R package called BTL Lassoo that does all that stuff that I've shown you. So, well, you have those main functions. This cross-validation is CV BTL Lassoo, okay? It's already implemented for you to get not only the pass, but also the cross-validated solution. Well, you can, in this package, include all the effects that I've shown you before, okay? You can include intercepts, you can include subject-specific effects, you can include object-specific covariates, you can include subject-object-specific covariates, okay? So team match-specific covariates, both with global parameters or with team-specific parameters, and you can include order effects in sports, home effects, both global, so that's equal for all the teams, or team-specific order effects. Okay, and then you can apply all the penalties that I've shown you. So you can apply penalties to cluster intercept parameters, to cluster and select variable effects, and to cluster and select order effects. What we usually do is use the so-called adaptive Lassoo, which was proposed in 2006, where you use additional weights. I don't want to go too much into detail about those weights, but yeah, the main idea is you estimate the unpenalized version of the thing you want to penalize, and you weight with the inverse of that, okay? Which means, well, if the maximum likelihood estimate is a very big value, then it's less penalized than if the maximum likelihood is a very small value, okay? Which has the sense that if the maximum likelihood estimate, for example, of two teams is already very similar, then we increase the penalization on the difference of those two. If the maximum likelihood is very different, for example, Bayern and Darmstadt, then we have a less strong penalization. Okay, and, well, you can include all those different covariate effects, penalization effects. I'm not going too much into detail now. I hope it got clear with the examples that I showed you, the applications. Just one or two last things about the package. So, of course, we have additional methods for plotting and stuff. And we also have the possibility to do bootstrap on the whole model, which means, well, we draw bootstrap samples, and then we apply the whole method again on the bootstrap samples, okay, including the cross-validation, which gives you then the possibility to draw bootstrap intervals for each of your estimated parameters, okay? So that's just an example of something we did. We include those market values. We allowed for team-specific home effects, and we have those intercepts. And then you see the bootstrap interval for the parameter here for Augsburg, for example, is that large, okay? Just to give you an impression about the uncertainty of the parameter estimates. But really not for something that you would call inference, or for testing, or for saying words like significant, okay? It's just for an impression of uncertainty. Okay. Well, it's implemented in R, as I said before. To speed it up, it's implemented actually in C++ and then included into R. What we did for those penalty terms, we approximate them by quadratic terms, which makes it easier because you can do Fisher scoring then. And both the cross-validation and the bootstrap can be parallelized so that you can speed that up, because obviously you can imagine that especially the bootstrap may take a pretty long time. Okay, so that is it. Thank you for your attention. Yeah, thanks. Yeah.
your match-specific covariates very well, like ball possession, because if you're using ball possession at the end, measured at the end of the match, you could also use the final score to predict the final score.
Well, of course, we cannot predict in the sense of prediction because we only know the covariates at the end, okay? This model for those on-field covariates is really, well, an explanatory model, okay? You can, we hope to posterior explain what led to the match that we've seen or what led to the outcome we've seen. Of course, we can not use that for like predict what the next match will be and then bet on it or something, okay? But prediction itself, you can easily do because you simply, so prediction in the sense of cross-validation, okay? Because you simply take out like 3 match days, you estimate the model on the rest of the match days, and then you predict your test data by just assuming that you know the variables, okay? But that's a statistical way of predicting and not predicting in advance of seeing the match.
Have you looked at the predictive success of your system for a set of games as to how often the higher-rated team beats the low-rated team, and maybe even a probability as compared to gambling lines? Have you done any of that?
Yeah, we did some of that in the paper. What did we find out? It was actually pretty good. We can really compare with the betting odds, but I mean it's not really a fair comparison, of course, because we know something that they cannot know. On the other hand, they know something that we don't know, like injuries of players or whatever. Okay, but no, it was actually better, right? It was actually better than the probabilities that were stated by the bookmakers. But again, it's not.
What kind of
fair.
probabilities of success have you had in predicting the winner of a match?
So we had like overall accuracy of 50%, which is when we reduce it to the 3 outcomes, right? Win, draw, loss. Just guessing would be like 33%, right? So we ended up with 50 or a bit above 50%.
What if you take wins plus half of ties? What's that, about 60-something? Or?
I don't know, maybe.
Okay. That's a good measure of success, wins plus half of ties, or the fraction of non-tie games that are successful.
By the ability of a team, so let's say with the objective of establishing a ranking of teams, you mean the intercept parameter. Isn't there the chance that team-specific ability is becoming mixed up with things you expect from big teams? So like, let's say a team that has a high number of shots on goal because they're good, like Bayern, then the team-specific parameters are going towards the coefficient of shots on goal for Bayern, and it's not in the intercept. So then maybe the intercept is failing to capture some of Bayern's ability for the ranking.
Well, that is actually something I left out. Maybe I should have talked about it. The thing is, we center those team match-specific covariates around the mean for the specific team, okay? Because, well, Gerhard wrote it down here. I don't know if it's that intuitive. Basically, it says it doesn't change the coefficients of those covariates It only changes the intercepts. Of course, you're right. It would change the intercepts if, like, the average distance the bion plays would have to be covered by this distance effect, okay? But it's centered so that all the average effects are already covered by the intercept, okay? Those two modes are totally equivalent, but we think that this is nicer because the other way around, as you said, the intercepts are a total mess, okay? They are not that parallel as you can see them here, but they would go up and down and whatever because of those correlations.